So last time we got the paperwork out of the way, so today we can actually start doing some cool stuff, some fun stuff. Yeah, so we're going to start off our semester here by learning about some of the tools that are useful for testing circuits. Throughout the rest of the semester, we're going to be building our own circuits, and we're going to try and figure out if they're working or not. So we're going to talk about some of the tools. We're going to spend a whole lecture tonight talking about the tools that are going to help us for the rest of the semester. So getting a chance to get familiar with them right away should really help you out. It should be a good investment for you. So that's what we're going to do. We're going to talk about oscilloscopes, function generators, and signal measurements. So we're going to start off tonight and talk about what these things are, why we care about them, and we're going to propose a mystery. What can these tools do to help us test our circuits? We've probably seen some of these tools a little bit before, but we're really going to dive in and try and use some of their more advanced capabilities tonight so you get familiar with those and you know how to use them throughout the rest of the semester. So we'll go into, in order to solve this mystery, we'll go into a little bit of theory about what signals are, how function generators work, and some of the advanced features of oscilloscopes. And then I'll give you a quick overview of tonight's lab and some of the things that I'm going to be looking for in the labs throughout the semester. Okay? So any questions before we get started? All right. So then let's dive right in. So what are these things? So let's talk a little bit about signals first. A signal is really anything that can contain information. There's lots of different examples. Speech is a type of signal. The sound of my voice contains information that you all hear and interpret. So speech and sound in general are signals. Light can be signals. When you talk about fiber optic cable, what that cable is doing is that it's carrying information in the form of light. So a light can be a signal. And then there are many different types of electrical signals as well. There can be signals encoded as voltage, signals encoded as current. So many different things qualify as signals. Okay? We are going to be particularly interested in electrical signals. Function generators create different types of electrical signals. They create different shapes of signals, different frequencies, different amplitudes, and we'll see how to adjust all of those and create those tonight. And then oscilloscopes measure electrical signals. In particular, they measure voltage signals. And they can show us what the signal looks like. They can also measure lots of things about it, like the frequency, the amplitude, and so forth. Okay? So we'll see how we can use oscilloscopes to measure those signals and how we can make adjustments to get the most precise measurements. Okay? So that's what these things are. We talked about what signals are, what function generators are, and what oscilloscopes are. So why do we care about these things? Well, we care about signals for lots of reasons. A lot of times we're setting up instruments or equipment to measure signals, whether we're measuring the amount of CO2 or carbon monoxide in the air, or whether we're measuring, water quality or seismic shaking. A lot of times we need to measure signals with equipment, and so it's important to learn a little bit about signals and some of the vocabulary that goes along with those, so we know how to describe them. Function generators are important because they help to create signals that can actually help us to test out our equipment. So function generators can often stand in for larger, more expensive, harder to use pieces of equipment. I'll give you an example. When I was working at the Lawrence Livermore Lab, I was working on a project where we had to count the pulses that came out of a laser. Now, this laser was the size of a room, and it cost several $1 million, and it was part of a production line, an assembly line. So it was being used all the time. So I had to write the software to measure the pulses, and so it would be very difficult for me to be right next to the actual equipment and testing my software on the real thing, because I would have to be interrupting the production that was already going on. I couldn't move it into my office. I couldn't get another one in my office because, frankly, it was larger than my office. So it was very inconvenient for me to actually test my software using the real device. So instead of using the real device, I needed something that could stand in for that. And a function generator did that nicely. It turns out that the way that the laser pulses were displayed from the actual laser was with voltage pulses. So every time the laser fired, a little voltage pulse was created. So instead of having the actual laser in my office to test my software, I just had a small function generator in my office that created the same size and shape of pulses. So I could write my software in my office, test it out, do 90% of the testing right there with this little function generator that cost maybe $100. And then, when I was pretty confident that things were working the way they should, I could take my software down and request a little time on the actual machine and do the last bit of testing. Okay? And that's a very common application for function generators. They stand in for some other type of signal that might be difficult to get or inconvenient or expensive to get. Okay? So function generators are very useful for testing out circuits. They are often used to inject a signal into a circuit in place of something else. Okay? So that's what function generators are. And then, so that's why they're important to us. They can take the place of more expensive things. Oscilloscopes are important because we need to see how our circuit is actually working. And oscilloscopes help us to do that. We often know what a signal should look like at various points throughout our circuit. And an oscilloscope can help us measure and see whether the signal is the way it should be at various points in our circuit. And this is very, very useful for troubleshooting, okay? If you know that you're supposed to have a sine wave at 50 hertz at this particular point in your circuit, you can put the oscilloscope there and check and make sure that it's actually there, okay? So oscilloscopes allow us to measure signals that change over time, and they can give us very precise measurements of these signals. So that's why those are important. Okay? That's why we care. So the mystery for tonight is, what can these tools do to help us test our circuits? So we're going to actually explore some of the details about how these tools work and how we can really use them. So any questions so far? Okay, then let's jump right in. Let's talk about some of the theory for signals, function generators, and oscilloscopes. So with signals, most of the stuff that I want to talk about is vocabulary. Okay? I want to talk about some of the important words that we're going to be using to describe these signals so that we're all on the same page and we know what we mean when we're talking about a signal. We know how to describe it. Okay? So there are various types of signals, or you can think of this as shapes. So if I drew a signal that looks like that, what kind of signal is that?
Sine wave.
Sine wave, yeah. Sine wave. If I drew a signal that looks like that, what kind of signal is that?
Square wave.
Square wave, perfect. If I draw a signal like that, what kind is that? triangle wave. Yep.
I've seen it referred to as sawtooth.
That's the next one, actually.
Okay.
A
I
sawtooth,
thought they were different.
Yeah, a sawtooth is a special kind.
Okay.
It goes straight up like that and then
drops.
Yeah, it goes
Right.
up at an angle and then comes down.
Oh.
Okay. Because I've had that.
Interesting.
Or
Isn't that like a
alternatively, it might go straight up and then come
diode?
down.
No, something discharging.
So this is a saw.
So it's called the same no matter which way it's pointing?
Right, right. Yeah, they're both called sawtooth. So these are a couple of the shapes of the waves. These are the most common. There are also, there are other patterns, but these are the most common ones. Okay. So there are also properties of waves. So there is an amplitude. So there are several different ways to measure amplitude, but it's basically how big the wave is. So one way to measure it would be from the top to the bottom. And we'll get into these different ways of measuring in just a minute. But the amplitude is how big the wave is. There's the frequency. And that is how fast the wave repeats. Or how often the wave repeats, I guess. This is usually given in hertz, or cycles per second. So if we say that a wave has a frequency of 60 hertz, that means that it repeats 60 times every second. Okay. So let's do a couple of examples of amplitude. So this would be a small amplitude wave. We could have another wave that was like this. That would be a large amplitude. For frequency, if we had a wave that was like this, that would be a small frequency. If we had a wave like this, that would be a higher frequency. I suppose low and high are better words to describe frequency. Low frequency and high frequency. Okay. Going along with frequency, there is another concept, which is the period. You guys probably can't see that in the back. Sorry. Let me move that around. The period is 1 divided by the frequency. Okay? So for instance, if you had the frequency was 100 hertz, then the period is 1 over 100, or 0.01 seconds. Okay. So any questions about period, frequency, or amplitude? Yeah, that's a great idea. Yeah. So the period is the amount of time from one spot on a wave to the same spot on the next wave. So from there to there, for instance. It's the length of time that it takes for one complete cycle to occur. Yeah.
Does it always have to be like from peak to peak, or can you do it from like the middle to the middle?
You could do it from the top to the top, the bottom to the bottom, middle to the middle, anywhere, as long as anywhere should be the same.
Okay.
Yeah.
I was wondering why the different shapes are used. Sine wave versus a square wave, triangle wave.
Oh. Why we have a function generator that can create those different shapes? Yeah. Well, different applications require different shapes. For instance, if you're talking about audio applications, sound typically comes in sine waves. So if you hear a pure tone, like from you pluck a string on a guitar, that tone is a sine wave at a particular frequency. So if I wanted to simulate that, I would need a function generator that could make a sine wave. Conversely, in the application that I talked about earlier with the laser, I needed to create square wave pulses for that. In terms of triangle waves, I'm not thinking of anything off the top of my head, but triangle waves could be used for other applications as well.
So
Yeah.
you use square waves because it's just on, off.
Yeah, exactly. So that's a great point. So digital technologies require things that are either on or off. And so if you're working with a digital system, often you will create square waves that are either on or off. Yep. Other questions? Okay. So that's the last piece of vocabulary that I want to give you is duty cycle. Okay? So duty cycle refers to square waves. And it is the amount of time that the square wave, or the percentage of time that the square wave is on.
Oh, okay.
Is on or is high. So for instance, if you had a square wave that was high as much as it was low, it was up for the same amount of time that it was down, that would be a 50% duty cycle, because it's on for half the time and off for half the time. If you had one that was on for most of the time and off for just a little, that might be a 70% duty cycle, say. And if you had one that was on for just a very short time and off most of the time, that might be closer to a 10% duty cycle. Okay?
So duty when it's actually doing something.
Yeah, that's a great way to put it. Exactly, when it's actually doing something.
So when you're looking at one of these in the oscilloscope, it'll tell you the percentage.
Yes,
Okay.
and we'll get to that in just a second. But yes, there is a way to use the oscilloscope to measure the percentage. Well, what it'll actually do is it'll tell you the amount of time that it is high. And then I think you'll have to do a little bit of math to figure that
Okay.
out.
You
the
have to
percentage.
measure, I think, if I remember right on the scope.
Yeah. Yeah, other questions? Okay, cool. All right, so that is a little bit of vocabulary about signals. So now hopefully, I know these are a lot of words, but hopefully when I start using these words, you can refer back to your notes or a picture or whatever, and they will start to click in your head and you'll know what those mean. Okay? So any questions about the vocabulary before we move on? Okay. So the function generator can create all of these types of waves. It can make all of those. You can set these properties. You can set the amplitude, you can set the frequency, and there's actually a way to set the duty cycle as well. Okay? So let me illustrate this on the board here. So this is going to be my function generator here. Can you guys see that color in the back? All right. So let's start off with the shapes, the types of waves, and talk about how to set those. So there are several rows of buttons. The second row of buttons down on your generator is like this, and these buttons have different shapes on them. So there's a shape that looks like this. That's how you make a sine wave. If you push the one that looks like this, it makes a square wave. If you push the one that looks like this, there's a triangle wave. You'll notice that there is not a button that looks like the sawtooth wave, right? So the generator can make sawtooth waves, but there's not a button for that. So there's a trick to do that, and I'll tell you about that in just a second. Okay. So, but these buttons make the sine wave, the square wave, and the triangle wave. Right? There is an amplitude knob. So to set the amplitude knob is down
Right
yeah,
next to the output.
Yeah. So this says AMPL, that stands for amplitude. And so if you adjust that, you turn it one way, it makes the amplitude larger. You turn it the other way, it makes the amplitude smaller. Okay? So there were a couple of other things that I wanted to say about amplitude. I wanted to tell you a couple of the ways that amplitude can actually be measured. Okay? So if you measure it from the very top of the wave to the very bottom of the wave, then that is called peak-to-peak amplitude. Okay? So it's called peak-to-peak because it's going from one peak to the other, the highest peak to the lowest peak. So that's peak-to-peak amplitude. If you measure it from the middle to the top, that is called simply peak. Okay, that's the middle to one peak, so that's just called peak. There is another one that is called RMS, that stands for root mean square. And that one is funny. It's not
Has
to the,
its
it's not,
uses.
yeah, it's not all the way to the top. It's about like this on a sine wave. So for a sine wave, RMS equals 0.707 times the peak amplitude. Okay? So if your peak amplitude was 10 volts on a sine wave, what would your RMS amplitude be?
7.07.
Yeah, 7.07, exactly. Yeah.
Why? Why would you need the RMS?
Right. So that's a good question. It's sort of a funny thing. Basically, if you have a 10 volt DC source and you put that into a heater, and then you have an AC source that's 10 volt RMS and you put that into the same heater, they generate the same amount of heat. So it's sort of like the equivalent amount of power between AC and DC.
So like AC has more power.
Well,
If you have,
It measures the amount of power that's actually usable, right?
also a portion of
Yeah.
AC is not usable. So
well, I mean, AC is fluctuating all the time, right?
Yeah.
So the average is actually 0. But it doesn't make sense to say that it has 0 power, right?
yeah.
It has these peaks where they go very high. So, it might have a 15 volt peak, but it's not the equivalent of 15 volts DC because it's not at 15 volts all the time. So it's somewhere in between.
Okay.
And the RMS is that equivalent. It's that in between point. Okay.
That's the best they can do, right? You see the parameters.
Most efficient.
Well, it's the
I
equivalence
Yeah.
to DC. Yeah.
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 I guess.
So
That's cool.
yeah, it's kind of a funny thing. And you might think it's such a funny measurement that it would never really be used, right? But it actually, it's always used. So when you hear about 110 volts coming out of the wall, it's 110 volts RMS. When you measure something with a digital voltmeter and you put it in the AC setting and you measure how much voltage, that measurement that you get out of the meter is in RMS.
Oh.
Yeah,
Oh, I didn't know that.
yeah.
So is there a way to actually set your? Do meters have a setting where you don't? Not at all.
Don't
Oh wow.
meter. I mean,
Just
at least not
oscilloscopes?
these meters. Most meters that have just one setting for, in fact, I believe all meters that have just one setting for AC give you that measurement in RMS.
And you can't catch the actual frequency. Not capable meter to catch the frequency to actually, get higher altitudes. That's
Oh no! It could. I mean,
we're just set to be RMS.
it's set to be RMS. Yeah, the companies
Just so people
set it
don't
up
do the
so
math.
that it gives you RMS. It is the most common measurement, the most common way to measure AC signals. Even though it's a really funny
Interesting.
formula to calculate it, it's the most common way that AC signals are quantified. So, yeah, so that's what's happening.
Well, makes sense. I mean, if that's what's used all the time, it makes sense that those will measure that.
Yeah. And we'll see in a minute that we can use oscilloscopes to measure all of these things. We can measure peak to peak, or just peak, or RMS. Okay. All right. So Getting back to the function generators, we can set the amplitude there for the signals. We can set the frequency of a signal. That is the big knob on the left-hand side. So it's like this, and it's got a little indicator for its position. So that is frequency. So you turn that one way and the frequency goes higher. Turn it the other way, the frequency goes lower. And there are frequency ranges as well. So these buttons along the top of your meter, or your function generator, are the frequency ranges. So this is the 1 hertz range. This is the 10 hertz range, and then 100 hertz and the kilohertz, and so on and so forth. So really, to set the frequency, you need to use the range and the knob together. You use the range to get yourself kind of in the right ballpark, and then you use the knob to fine-tune that and get it to exactly what you want. Yeah?
Is there a way to get lower than 1 hertz?
The actual frequency is the product of the range and the knob. So the knob, I think, goes down to like 0.3 or 0.1 or something. So you could probably get it down as low as 0.1 hertz.
Okay.
But I think that's the lowest that it goes.
Cool.
Yeah.
Slow.
Yep. Yep.
0.1.
Okay, so that's how you set the frequency. And then there is one other knob. Well, there's a knob for the duty cycle. Okay. So the duty cycle is right around there. And in order to use that, you have to pull it out. So normally, it's pushed in, and it doesn't have any effect. When it's pushed in, you can turn it left and right, it makes no difference. In order to actually have it take effect, you have to pull it out. Yeah?
And it only works with the square waves?
Not quite.
Oh.
Actually, that is the key to the sawtooth wave. Okay?
Oh.
So if you have a triangle wave, and then you pull out the duty cycle, and you turn it one way, it causes the triangle wave to lean over and become a sawtooth wave in one direction. If you turn the knob the other way, it leans the wave the other way, and it becomes a sawtooth in the other direction. Okay? With the square wave, it does just what you imagine. It sets the amount of time that the square wave is high. And then with the sine wave, it does some weird stuff. It kind of leans the sine wave one way or the other also. Okay, so you can play around with that and see how it affects the different wave shapes, but that's the duty cycle. And then the last knob I wanted to tell you about is the offset knob. So the offset is next to the amplitude there. The offset determines whether this wave is centered right around 0 or whether it gets shifted up or down. Okay? So again, you have to pull the knob out in order for it to work. Normally, it's pressed in and it has no effect. The wave is just centered around 0, but when you pull it out, then you can actually use it to move the wave up or down. Okay? Yeah.
So if you pull it out and you're adjusting it and you want it to go back to center, you just push it back in?
Yep.
Okay.
Yep. And as soon as you push it back in, your wave just gets right back centered around
Nice.
0. Yeah.
So why might you move it up and down?
Yeah, so that's a good question. For instance, with the square wave, there's a standard called TTL, or transistor to transistor logic. This is a standard that a lot of digital devices use when they're talking to each other. And it specifies that the devices create square wave pulses that are either at 0 volts or 5 volts. So if you wanted to replicate something like that with a function generator, if you didn't have the offset knob, you could create a square wave, but it would be centered around 0. So half of the time it would be negative, and the other half of the time it would be positive. So you need the offset knob to pull that up so that the bottom is at 0, and then you can adjust the height to make the top at 5 volts. Okay. So that's one example. There could be other examples as well. Other questions? Yeah.
What's the CMOS switch for?
So there's, let's see. Yeah. You know, I'm not sure what that one's for, actually. That's a good question. There's a Cmos knob on the function generator, and I don't know what that one does. So I'll have to look that up and see if I can find
Well, it
out.
goes from 5 to 15 volts.
Yeah.
Says TTL.
Does that, I wonder if it means it's running through a CMOS?
You know, yeah, I'll have to look that up, and maybe I can get back to you guys after the break. Okay. Yep. Good question. Other questions? Okay. So those are the main controls that I wanted to talk about on the function generator. If you guys can figure out how to use those, you're going to be in good shape, and we're going to get some practice using those in tonight's lab. Okay? So now we've talked a little bit about signals, a little bit about function generators. So now I'd like to talk a little bit about the theory of oscilloscopes. Okay? How we can actually measure these different types of signals. All right. So
Maybe that adjusts the output for the TTL CMOS.
all right, so like I said, the oscilloscope is a device that helps us to measure all of these properties about signals. So let's just draw the basic screen that you might see on an oscilloscope. So the screen looks like this, and there are these vertical and horizontal lines going across the screen. And they break the screen up into boxes. And each box is called a division, and these divisions help us to visualize how big our signal is, certain properties about our signal. So they give us we can look at these divisions and kind of estimate certain things about our signal. And it's really important to be able to do that to get a rough idea about what's going on, okay? So, so on our screen here, the y-axis, the vertical axis, is voltage. And the horizontal axis here is time. And these boxes represent increments of voltage and time. So down at the bottom of the screen, there is always a little field that tells you the volts per division. And then another one that specifies the amount of time per division. Okay? So we can look at those and look at our signal and get an idea about what's going on. So let me give you an example. Let's say that we had a signal that looked like this. It was a sine wave that looked like that. And let's say that we had 5 volts per division and 100 milliseconds per division. And then I asked you, what is the peak amplitude for this signal?
Just peak.
Yeah. Yeah, exactly. It's 10 volts. And we can tell that because, remember, the peak amplitude is the distance from the middle to the top of the wave. We see that there's 2 divisions from the middle to the top, and there's 5 volts per division. So that's a total of 10 volts from the middle to the top. Yeah.
What if the wave doesn't end up like perfectly, on the division? How do you measure it?
Right. So right now we're just talking about kind of eyeballing it and getting gross measurements. So, or getting an approximation. In a minute we'll talk about how to get a more precise value. So, but you can still eyeball it even if it doesn't land quite there. So, say it landed kind of halfway in between. You know that there's 5 volts per division, and it was 2.5 divisions. That would be like 12.5 volts, right? If it was closer. Yeah, so you can still get a rough idea. And we'll talk about some techniques for getting more precise measurements in just a second. So we can say that the peak amplitude here is, in this case, 10 volts peak. What about the period? Can we estimate the period here?
Yes.
Yeah. What would the period be?
400 milliseconds.
Yeah, exactly. So remember, the period is the time from one spot on a wave to the same spot on the next wave. So we could look from here to there, for instance, and then we could count how many divisions there are in between those 2 positions. So in this case, there's 1, 2, 3, 4 divisions. And so at 100 milliseconds each, that is 400 milliseconds for the period. So here's a tricky one. Can we figure out what the frequency is now?
Yes.
Yeah. Can we do that just by looking at the graph? Or do we have to do a little math?
We have to do some math.
Yeah, a little math. Okay. You guys remember what the formula was for the frequency?
No.
One divided by frequency. Oh, the opposite?
Yeah, so this is the formula for the period. It turns out that the other formula works pretty much the same way. So we know that the period is 400 milliseconds, so the frequency should be 1 over 400 milliseconds. So what does that come out to be?
Some of us need calculators.
So this is 1 over 0.4 seconds, right?
I got 2.5.
2.5.
Samsung Experience Home. Screen off.
2.5 hertz. So this wave repeats 2.5 times every second.
Oh.
So we can figure all that out just by looking at the graph. So there's a whole lot we can do just by eyeballing it, and we can get pretty good approximations. And these are actually really important because, sorry, before I go on, does anybody have questions about how we did these measurements or how we did the calculations? So just to recap, we counted 4 divisions at 100 milliseconds each. So that came out to be 400 milliseconds. 400 milliseconds is the same as 0.4 seconds. So we said the frequency was 1 over the period, so 1 over 0.4, and that comes out to be 2.5.
I thought it was 0.04. Never mind.
Yeah, a milli is 0.001.
Yeah, right. Okay, got it. I understand what you're saying. Never mind. Got
Okay,
it.
cool.
Got it in my head.
Yeah.
Thank you. The math worked out. So I'm good. I'm happy.
Good, okay. All right. So it's important to be able to look at the screen and get an approximation of what you think the wave, or what you think some of these measurements should be. We'll see some more precise ways of making these measurements, and you might think, well, the computer already does it for me, why do I need to know any of this stuff? But it turns out that the computer makes mistakes sometimes. And if you don't have a rough idea of what the answer should be, you might just be taken in by those mistakes, and you might not realize that something was not working right. Okay? I'll give you an example. Sometimes waves are not perfectly smooth like this. So sometimes, instead of being a really nice sine wave like that, it might come out to be a sine wave that looks more like this. And you're still trying to measure the frequency of the whole thing. But when you ask the computer to make the frequency measurement for you, it might look at this and say, oh, this has got a lot of frequency there. I'll measure that frequency. Okay? And so you can end up seeing, it'll give you a frequency measurement, but it'll be the frequency of the noise rather than the signal you actually care about. Okay? And if you didn't look at this graph and understand what was going on, you would just have that one number and you would say, you'd have to trust that. So it's important to look at this. Also, when we talk about measuring amplitudes, the computer will measure the peak-to-peak amplitude of your signal. That means that it will take the very highest point on your signal and the very lowest point on your signal and measure the difference between those two. So if you've got noise like this and you happen to have a little spike up there like that and a little spike down there, then your amplitude might end up measuring like this rather than like that. Okay? So you need to be aware of those things. Yeah?
So is that jagged line, is that representing like unwanted interference? Is that what it usually is? Or?
Yeah, often. Sometimes when you're dealing with very small signals, you can pick up noise from radio signals and things like that that are just present in the air. Yeah. It just depends on your signal. Sometimes that little tiny wave is the part that you actually care about, and so then you have to figure out how to measure that. It just depends. That's where your knowledge of the circuit and what's going on inside of it is really key.
Yeah, because I had that happen.
Yeah, it happens. So that's why it's important to be able to look at the screen and get a general sense of what you think your signal measurements should be, and then you can use the scope to be a little bit more precise and get some finer grained resolution on those measurements. So any questions about how to kind of get the big picture here? All right, so then let's talk about some ways that you can be more precise and use some of the features of the scope to actually measure some of these details. So, so there are two main ways of measuring the frequency and the amplitude and things like that. There's the measurement mode of the scope, and then there are cursors, okay? So let me talk about those. So with the measurement mode of the scope, the way you get into that is that on the top of the scope, there's this button over here that is labeled measure.
Oh, see.
And when you push that, that's going to bring up a menu that has lots of different measurements in it. And then you can choose which one you want. So you can choose things like peak amplitude or peak-to-peak amplitude, or RMS amplitude, or frequency, or period, or lots of others. They actually have some related to duty cycle as well. So they have time high, things like that. So if you push this measure button, you can scroll through those different options and then choose the one that you want. And you can have many different measurements up on the screen at the same time. Yeah?
On the newer ones, this one right here, it's different from this header here, which will get a better one.
The one actually that you're pointing to on the left is a fancy function generator, believe it or not. So the oscilloscope is the one on the right. Yeah. So yeah, we can digress into the function generator there. That, I believe that's actually called an arbitrary waveform generator. So.
Oh, that's what that is.
Oh yeah, it's around top.
I
Yeah.
knew it was a generator, but I didn't know how it was doing.
Yeah, so that's sort of an even fancier version of a function generator. So that one allows you to use more shapes, and it can also create a specific number of pulses. So that's the type of thing that I used at Livermore. I knew that the laser would create about 1,000 pulses, so I would program the generator to create only 1,000 pulses, and then I would measure it with my program, and if my program counted 1,000, I knew that things were going well. If it counted 5,000 or 200, then I knew something was wrong.
999.
Yeah, right. Yeah, exactly. So basically, the arbitrary waveform generator is like a function generator on steroids. So it's even more powerful, but we're not going to go into those. We're probably not going to use those this semester. Okay. Back to the oscilloscope. The measure button on the top allows you to measure all those different things, and it just creates small readouts down at the bottom of your screen that have those measurements listed. So you can see the peak-to-peak amplitude and the frequency and the duty cycle, or the time high, it all displayed at once if you want. You can choose whichever ones you want. So that's one thing. If you have a nice clean signal, the measure function is the easiest way and the quickest way to get those measurements. Okay? Sometimes when your signal is like this, the measure functions get confused, like I already mentioned.
Mm-hmm.
So in that case, sometimes you have to use a different way of measuring your signal, and that's where cursors come in. So again, yeah, right underneath, thank you, right underneath the measure button, there is a button that's labeled cursors. And if you push the cursor button, it will create these lines that go across the screen. So you can either have vertical lines or horizontal lines. So you can set these cursors to various points that are interesting to you. So if you had a noisy signal like this and you wanted to measure from there to there, you could use cursors and move them until they were at the spot where you think is the top of the signal and the bottom of the signal. And then over on the right-hand side, it gives you 3 pieces of information. So it gives you V1, V2, and then delta V. Okay? So V1 is the voltage for cursor 1. So that would be like the position of this top one. V2 is the voltage for cursor 2, so that would be like the voltage of the bottom one. And then delta V is the difference between the two. So this little triangle is the Greek letter delta, and whenever you see that, it most often means difference. So delta V is the difference in the voltage between these two cursors. So you can set the top cursor where you want and the bottom where you want, and then it'll give you a measurement of exactly how much voltage is between those two. Yeah.
So you probably want to use something like this when you have a bunch of noise, like that picture.
Exactly. Yeah. When the measure button is getting confused and giving you weird numbers, then you can try the cursors, and you might get more accurate measurements that way. Yep. So you can have horizontal cursors like that. You can also have vertical cursors. So you can only do one at a time, but you can choose horizontal or you can choose vertical. If you choose horizontal, it will give you the voltages. If you choose vertical, yeah, it'll give you the time, exactly. So you can set a cursor there and a cursor there, for instance, and that'll give you time for the first one, time for the second one, delta time, so the difference between them, and then it will also give you the frequency. So if you set one cursor at a certain point on a wave and then the next cursor at the same point on the next wave, then what's another name for the difference in time between those two cursors? The period, exactly. So the oscilloscope assumes that you've set one you've set them one period apart, and then it calculates a frequency based on that assumption. Okay? So
That's cool.
yeah, so that way it's just one less
Just math.
formula you have to do, a little bit less math. Yeah. So any questions about that? Yeah.
On ours for the V1, V2, when I move the V2, it's moving top button, and when I move V1, it's moving the bottom. You would say it's the other way around. Is there a button on there that I go backwards or?
No. So when you move V1, it'll move one of them, and when you move V2, it'll move the other one. You can actually cause V1 to be on the bottom or V1 to be on the top. It's just up to you. Yep. Other questions? Okay. There are a couple of other key pieces of information that we need to have. One is the zero level. So there is a little arrow that's on the right hand, or I'm sorry, on the left hand side of your screen, and this is the 0 level for that particular wave. So this shows you where 0 voltage is for that wave. Oftentimes, it'll be right in the middle of the wave, but it doesn't have to be. Remember we said that we could have that offset knob on our function generator, so we could move that wave up or down. So the 0 level might not be in the middle. It might be down here. Or it might be, way up here. Okay? So it can be anywhere here. And that tells you where 0 volts is. So let's say that the 0 level was right there. What would be the maximum amount of voltage that I was getting? Suppose we're back to the nice clean signal and it was going up there.
-5?
Yeah, exactly. So this would be -5 volts. And what would be the lowest voltage down here?
20? Maybe 20?
Yeah, -5, -10, 15, -1. So yeah, this would actually be -25 volts down there.
Oh, yeah.
Yeah. So if 0 volts is up there, then I know that my whole signal is negative, right? If 0 volts had been down there, then my whole signal would have been positive. So we're going to be asking you to draw these signals in your lab books. You're going to be looking at the screen on your oscilloscope, and you're going to be asked to draw these in your lab books. So when you're drawing them in your lab books, what you're doing is you're recording enough information so that you could come back and look at this in 10 years and be able to know what was happening on that screen. You know what that signal was like. So in order to do that, you need several pieces of information. You need to know how many volts per division you have. You need to know how much time per division you have. That gives you an idea of how big the signal actually is. And then you need to know where the 0 volt level is. There's one more thing you also need to know, and that's the trigger level. Okay? Yep. So there's another arrow on the right-hand side of the screen, which is the trigger level. So it can be, you can set it to be anywhere on the screen, but this is the trigger level. What's happening with the trigger level is that this kind of goes, we need to take a brief detour into how oscilloscopes actually work, okay, and what they're actually doing. Basically, what oscilloscopes are doing is they're acting like a camera that's taking pictures of your wave. And it takes picture after picture after picture, and it refreshes the screen every time it takes a picture. Okay. Now, if it was just taking pictures kind of at random times, then your wave might be kind of scooted over to the left at one time and then scooted over to the right at another time. And so if you put those right on top of each other, it might look like your wave is going all around back and forth. And it would be really hard to look at it and see what shape it is and do these measurements. So what you want is, you want the wave to be in the same place on the screen every time, so it just keeps lining up every time in the same way. And it looks the same to you, and it makes it easy for you to see what's going on and make the measurements. So the trigger is the thing that tells the oscilloscope when to take the picture of your signal so that those pictures line up on top of each other the same way every time. So what's happening with the trigger is that this is setting like a threshold, and the oscilloscope waits for your signal to cross that threshold, and then as soon as that happens, that's when it takes the picture. Okay? So if you set a trigger level here, then it waits for the signal to cross that trigger level, and then it takes a picture when the signal crosses that trigger level. Yeah?
Does it take it on the way back down also?
You can set it. You can set it so that it either takes it when it crosses the level going up or when it crosses it going down. You can choose which one, but it's one or the other at a time.
What, how high of a frequency can these things read?
Each oscilloscope model has its own frequency. I think it's specified on the top. I think it goes up to like
100 megahertz. So.
yeah, 100 megahertz.
Okay.
So yeah.
So it would make more sense to actually measure at the bottom because it's up time. So it's like, a certain amount of time to take a picture. Or
Well, you're just specifying the
or a
voltage
choosing
that
point
it has to
on
cross.
that, or a choosing point on the way, which is certain voltage. So it's pretty much taking pictures that are certain voltage over time.
Right, exactly. So yeah, every time it crosses that voltage, you take a picture.
Okay, that makes sense.
Yeah, so because of that, this trigger level has to be between the top and the bottom of your wave, right? If it's somewhere in there, then you know your wave is going to cross that trigger level at some point and cause the picture to be taken. If the trigger level is up here, then the wave is never going to hit that, and it's never going to cause it to be taken. So what happens is that if the trigger level is up here too high, then the voltage never crosses the trigger, and after a certain amount of time, the oscilloscope says, it's been too long since I've taken a picture, I'm just going to take it. And then you get that effect where the pictures don't line up, and the wave is kind of going back and forth on your screen like this. So if you end up in that situation where the wave is going back and forth like this and it's not standing still, that typically means that your trigger level is either too high or too low, and you need to bring it back between the top and bottom of your signal. Okay? And so trigger level is another thing that you need to show on your diagram when you record that in your lab book. So those are some really important things to include. Often when you're writing in your lab book, you will also want to include the period, an indication of where you're measuring the period and how long that is, and then some indication of the amplitude. So, for instance, you might go like this, there, and draw some arrows, and say that that is 20 volts peak to peak. Peak to peak is often abbreviated PK-PK. Okay? So just to recap, when you are drawing things in your lab book, I try to always use pencil because I always screw it up. Honest to God, I draw it and then I look at it and something's always wrong. So I would use pencil. It's easier to erase. We don't care about, making sure that it's indelibly marked and can't be changed. It's much better to do it in pencil. So include the volts per division, the time per division, the zero level, the trigger level, the period, and then the amplitude. Okay. So questions about the oscilloscope? Okay. All right. Also, when you're drawing your signal, try to make sure that it covers the correct number of divisions. So if it goes up by 2 divisions on your screen, make sure that it goes up by 2 divisions in your lab book. If it's 4 divisions from the top of one signal to the top of the next signal, make sure that it's that big in your lab book also. Yeah?
How do you change the volts per division and the time per division on the oscilloscope?
Great question. Yeah. There's a knob for each one of those. Okay. So on the far right-hand side, there is a knob that says seconds per division. And this adjusts the number of seconds or milliseconds that you have per division. You could also think about this like zooming in and out in the horizontal direction. So if you turn it one way, it's like zooming way in. If you turn it the other way, it's like zooming way out. And there's another knob that there's actually an amplitude knob for each channel. So these oscilloscopes can measure up to 4 different signals at a time, and you can adjust the amplitude of each signal independently.
Wow.
So for each signal, there's a knob that is labeled volts per division. And these knobs are like zooming in and out in the vertical direction. So you can zoom way out and you can see the whole signal, and then if there's one part that's particularly interesting, you can zoom way in on that part and just get a much bigger picture of that part.
Wow.
And then there's one other feature that I wanted to point out about oscilloscopes, and that is called the coupling. So there's AC coupling and DC coupling. And you can change that. I think that is actually one of the menu buttons that's on the right-hand side of the screen. So it's not labeled specifically, but one of the menu buttons on the right-hand side will allow you to change the coupling. So let me do a quick diagram here to explain the difference between AC coupling and DC coupling. So imagine that you have a signal that looks like this. It's got this wiggly part to it, and then it's also got this offset. So it's not centered around 0. So we say that the wiggly part of the signal is the AC part of the signal. And the offset is called the DC part of the signal. So from sort of the middle there to the 0, that's the DC part of the signal. So DC coupling shows you the signal exactly the way it is in real life. Okay? So if you looked at this signal with DC coupling, you would see it and it would look just like that. But now imagine that you didn't really care about how much offset you had. What you were really interested in was this little wiggle. So you wanted to find out more about that wiggle, how big it is, what frequency it is. Well, if you looked at it with DC coupling, and you tried to zoom in, what you would do is you would start zooming in around 0 volts. So you would focus and zoom in down here, but your signal's up there, so you wouldn't see it on the screen. Okay? So that's where AC coupling can be useful. What happens is that if you looked at the same signal under AC coupling, it gets rid of the DC part. So all you have left is that little wiggle. So this is how the signal would look under AC coupling. So now you've gotten rid of that DC part, which you didn't care about anyway, and now you can zoom way in, and you'll just be looking at the wiggle, which is the interesting part. Yeah?
So, is that big one on the left, is that AC coupling?
Well, in this case, it would have to be DC coupling because 0 volts is up here, and the signal is shifted down. If it was AC coupling, the signal would be centered around 0 volts. So oftentimes, you can look at the same signal under DC coupling and AC coupling to learn different things about it. So you might look at it under DC coupling first and measure what that DC offset is, and then just write that down somewhere so you know it, and then switch over to AC coupling so you can zoom in and figure out what your frequency is and your amplitude of the little wiggle and stuff like that. Yeah?
What would you need to know the DC offset for?
I mean, again, it just sort of depends on what sort of, yeah, what sort of signal you're dealing with. Sometimes the DC offset is the interesting part, and you've just got a little bit of noise there. So like if you're measuring a signal that's coming from a sensor, and the average voltage tells you how much sunlight is hitting a particular sensor, say, then that average voltage would be the DC voltage.
Okay, I got you.
Yeah, but sometimes you have a sensor that tells you how fast a wind vane is turning by what frequency your little oscillation is at. So then you have to measure the frequency of the oscillation.
Yeah, cool.
Yeah. Other questions? Yeah. Yeah, ground coupling. So thank you. That's a third type. Ground coupling. It just sets the signal to be at 0 volts. Okay. So if you're looking at your oscilloscope and you had 0 volts up here and you set it on ground coupling, then you would just get a green line that was perfectly flat right there. Okay? So that's useful mostly for finding a signal, finding where your 0 level is.
So with that, if you got a signal on that, that means you have a ground fault? Or
No,
something?
so you can choose what type of coupling you're using. So you can
Okay.
choose to have DC coupling or AC coupling or ground coupling.
Okay,
And if you choose to have ground coupling, then it always just sets your incoming signal to be 0 volts.
okay.
Yeah. Yep. Other questions? Okay, so I know that was a lot to take in, but that was a brief, somewhat brief overview of oscilloscopes. A long-winded overview of oscilloscopes. How about that? So let's go on and do a quick lab overview, and then I'll let you go and take a break for a while. Okay? So again, remember to record everything in pencil. I already talked about showing the signal correctly. I wanted to mention one thing about the leads that you're going to be using for the oscilloscopes. So first of all, we have two types of leads, one for the oscilloscope and one for the function generator. Okay, they both have the same type of connectors on the end. These are called BNC connectors. So it is physically possible to connect the oscilloscope lead to the function generator and the function generator lead to the oscilloscope. But if you do that, if you screw them up, then you will not get good measurements. Okay, so this is the fancy one. This is the oscilloscope probe. It's got a big connector on one side, and then it's got a little alligator clip on the other side. The alligator clip is the ground clip. The big clip is the one where you connect it up to the signal that you want to measure. Okay? The oscilloscope probes, while we're talking about them, have this little switch, and this is going to screw you up. This is going to screw you up a lot, all right? I can't count the number of times that this has really been a problem for people, including myself. This little switch goes between 1x and 10x, okay? You always want it to be in the 10x setting.
Which is down?
Which is
Down,
closer
away
to
from the point?
away
Okay.
from the point. The problem is that when you're pushing on the probe, you're pushing on the little switch, which pushes it into the 1x setting. And if you push it into the 1x setting, then all of your measurements on the oscilloscope are going to look 10 times bigger than they actually should be. Okay? So the little switch needs to stay in the 10x setting all the time. If you're expecting a 5-volt signal and your scope is telling you you've got a 50-volt signal, it's probably because the switch is in the wrong place. So you didn't have this type of probe in 302 when you're using the oscilloscopes over there. So you guys didn't have to think about that, but this is what's going on here. So always leave that little switch in the 10x setting. Yeah.
Is there a reason you'd ever want to change that switch?
Yeah. So if you were measuring very large signals, or can't remember if it's very large or very small signals, then you can move the probe or the switch over, but then you also have to change a setting on the oscilloscope at the same time. And if you do both of them, then you can get accurate measurements. But it's not something that we need to do in this class. Yeah. So that is the oscilloscope probe. This is the function generator probe, right? It again has a BNC connector, but it's got these two alligator clips on the end. The black one is for ground, and the red one is for the signal. Okay? So this one is the function generator, the other one is the oscilloscope probe. Try not to get them confused. Questions about that? Right, so that was the lab overview. Done with that, now you guys can take a much-deserved break.